Hi, hello and welcome to this lecture on semantic segmentation. Semantic segmentation is a very powerful technique from the broad range of deep learning architectures, and in this case the predictions of the classes are performed for each pixel rather than for a complete image. Before we spoke about classification problems in which you pass in an image to the algorithm and the algorithm is providing some output. Something like what is to be seen on this image, just some label. And in here, it's providing some label, but not for the complete picture, but for each and every pixel. So you can imagine this is much more powerful and much more demanding than just pure classification. So this kind of technique is applicable to many different fields. So for example, for medical imaging it is used, or for satellite image processing. And especially if we speak about autonomous driving, this is the technique to go for. Just some clarification. There is semantic segmentation and instance segmentation. And the difference you can see on this image, or on these two images. At the left-hand side, you can see the semantic segmentation. So you can see different objects on this image. Something like different cars, or the street, or street signs, persons, and all this. Whereas on the right-hand side, you can see an example for instance segmentation. It's pretty similar to semantic segmentation, but in this case, you don't just see different cars and the shapes of the cars are put into a certain class. Actually, the task of instance segmentation is to be able to predict each and every instance, so the different cars altogether. But here in this video and in this lecture, we will just focus on semantic segmentation. And here you can see one setup that you could use for this kind of architecture. This one that I'm going to show you right now and that we're also going to code in our lecture is called unit. And unit just because of the letter U, because it's having a similar shape to just the letter U. You can see here the symmetrical topology, and you can also see there are three different parts. There is a contracting path at the beginning, then some bottleneck path, and some expansive part. So in general, this kind of algorithm keeps the local information in this field of the contracting path. So at the beginning, you're starting with your image, and you do all the steps that we did in image classification, something like convolutional layers application, and then some pooling layers application, and then bringing this to the next level. And then you kind of unpool the information with some reverse functions at the right-hand side. So this algorithm is able to keep the contextual information in the expansive path. Another good feature of this algorithm is that images of different sizes can be used. And if we speak about semantic segmentation, we also need to speak about the loss function. Because in this case, you typically would apply a loss function called die-score. Or in total length, it's called Sørensen dice coefficient, because two different persons have developed the same idea more or less at the same time. And then you can see here the equation for this. So that's the dice-Sørensen coefficient, which is defined by this formula. You could also write it in our terms of machine learning terminology with true positives, false positives, and false negatives. Where in this case, it's easier to understand if you think about the true positives as the number of pixels that are common to both images. So you have, in the end, two images that are used for calculating the loss. One is the mask, so the true information, how the different classes should be visible on some processed image. And you have some prediction from the algorithm. So the true positives are the pixels where the prediction equals the mask information. Then we have the false positives. This is just the number of the pixels that is only applicable to the mask image. And we have the false negatives, which is the number of pixels that is common to the prediction image. And in general, this Sorensen dice coefficient evaluates the similarity of different samples and is able to measure the similarity over a complete set. So that's what it's doing. It's taking two different images and calculating some loss score based on two different images and each individual pixel of this image. And before we start with the lab lecture, just a few words about the data that we are going to use. So the data is coming from the so-called INRIA aerial image labeling dataset. You can see the URL here, and it's having 810 square kilometers of satellite images with a rather high resolution of 30 centimeters. And there are two different classes. So there are two different ground truths. The mask image could be either referring to a building or that there is not a building to be seen. And the images are covering a very broad range of different settlements. So it could start from very densely populated areas like cities, and it's going all the way to very old-fashioned alpine towns. So it's trying to be able to cover all different types of settlements. And here you can see some example. So at the left-hand side, you can see the raw image coming from some satellite measurement. And then you can see the masked information. So you can see we only have two different colors. Black referring to the class that there is not a building to be seen. And in white you can see that a certain building with the outline shape of the building is to be seen at this specific location. Alright, now we have some rough estimation of what we're going to do. We will take these images, sample them because they are way too large to use for training, take smaller samples out of these images, and train some algorithm based on UNet. So that in the end you can pass any satellite image and you trained your first classifier that is able to predict buildings on satellite images. I think that's a very interesting technique, and I'm really looking forward to the coding section. I hope you too as well. See you there.